Okay, so today we're going to go over the first type of graph, the type of graph that our lab tomorrow will be about, and that is position versus time graphs. Okay, we looked on Friday at how we build graphs and how we use y equals mx plus b to calculate stuff from those graphs. And so we're going to look at specifically today the position versus time graphs, and if we have time, we'll also look at velocity versus time graphs. Okay, so on a position versus time graph, here's what we can see. Okay, we can see where the object was at various points in time. Okay, so that means that we can see its position, and we can see when it was there. Everybody with me so far? Okay, from that graph, we can calculate a few things, and we can interpret or infer some things as well. So the point of today is to be able to read these graphs and interpret, infer, and calculate some things from them. Okay? The point here is not to memorize as much as it is to be able to use these skills on every kind of graph. Okay? And the reason I say that is, in Science 10, you're going to have like 2 or 3 different graphs that you're going to have to know. You could easily memorize everything you need for those 3 graphs. But when you get to Physics 20, you're going to have a dozen graphs. And when you get to Physics 30, you're going to have 3 dozen graphs. It'd be pretty hard to memorize everything from that many graphs. Okay? Oh, my whole respiratory tract is full of pork chop. Okay. All right. So if we're looking at this graph right here, the first one on the left, okay, what is that graph telling me about where the object is between 0 and 1 second? Where does that graph say the object is at time 0?
20 meters.
At position of 20 meters. Okay, that's where it is. And after 1 second, where is it?
20 meters.
Still there. What did it do for the first second?
Not moved.
It didn't move. Yeah, it did nothing. For the first second, it did absolutely nothing. Okay? Anytime you see a horizontal line on any graph, doesn't matter what it is, it means nothing's happening. Well, I shouldn't say nothing's happening. Nothing's changing. It means that something is constant at that point. Okay? Everyone okay with that idea? That could mean the position is constant. If that's the case, the object's not moving. It could mean the velocity is constant. That means the object is moving, but it's not changing the speed at which it moves. Or it could also mean that if this was a plant growth graph, that the plant's not growing. Doesn't mean the plant's dead, it just means it's not currently growing. It could be wintertime or something like that. Okay, so anytime we see a horizontal line, there's no change happening. Okay? Doesn't mean there's nothing happening, it just means there's no change happening. Okay, between 1 and 3 seconds, what's happening?
It goes up by 2.
Okay, goes up by 2 seconds. Yeah, it goes up. Yeah, 2 seconds pass, and what happens to the position?
It increased 40 meters.
Yeah. The position changes by 40 meters. It goes from 20 meters to 60 meters. We would have to assume that's forwards, probably. Okay, so it moved forwards 40 meters during that time. Okay. Did it do that at a constant rate? It appears to. In the first second, it went 20 meters. Okay. In the second second, it also went 20 meters. If each second it went 20 meters, how fast was it going? 20 meters per second. Okay, now here's how we can figure that out mathematically. What was its displacement during that time? Tab, what you told me a minute ago. 40 meters, right? It went 40 meters, and it did so in how many seconds? 2. Okay, is velocity displacement divided by time? meters in 2 seconds. Is that 20 meters per second? Okay, so that means the object was traveling at a constant velocity of 20 meters per second. Okay, everybody all right with that? Okay, so anytime we see a diagonal line, it means that there's a uniform change or a constant change in y over x. Okay, in this case it means the object was traveling at a constant velocity and also a constant speed of 20 meters per second. Everybody all right with that? Okay. All right, what was going on between 3 and 4.5 seconds? Nothing. Okay. The object stood still at a position of 60 meters. Okay, what is it doing between 4.5 and 6 seconds?
Going down like 15 meters.
Is it 15 meters, or do we know exactly how far it goes down? It is going down, for sure. How many meters?
40.
40, yeah. It goes from 60 back to 20, right? So it's now gone backwards 40 meters. Okay, did it do that at a faster or slower rate than when it went forward?
Faster, slower. I don't know.
Okay, well, in this part here, it went 40 meters, but it took 2 seconds. Here it went 40 meters, but it only took 1.5 seconds. So did it go faster backwards than forwards? It did. Okay, can I figure out how fast? Yeah, I do this again. V equals d over t. Okay, we said it went 40 meters backwards. That would be negative 40, and that took 1.5 seconds. Okay, so 40 over 1.5, was that 30? It's not. I should have fired up my calculator before I got started. I was too busy coughing. Okay, 40 divided by 1.5. Okay, 27 meters per second. Negative 27 meters per second. Okay, why is it negative? Which direction do they go?
It's negative because it's going down.
Yeah, it's going down or backwards, right? I mean, they don't really tell us up or down on this graph, but we could certainly say negative or backwards. It's backtracking for sure. Okay, let's think about the example we did last week with the trip to Walmart. Okay, when I went to Walmart and back, my total distance was, I just added how far it was to Walmart there and back. Okay, but when I got back home, what was my displacement?
0.
Right, it was 0. Okay, because my final position and my initial position were the same place. Okay, is that also true on this graph? Okay, my initial position is 20 meters. My final position is 20 meters. What's my total displacement? It's 0. I started and ended at the same place. Okay? One of the things that we can calculate off of a position versus time graph is displacement. Okay? And the way that we do that is we go final position minus initial position. Okay? Since they're both 20, 20 minus 20 is 0. Okay, so what was my average velocity over the whole trip? Chase is giving me the goose egg. 0, okay? Why is it 0? Because velocity is displacement divided by time. And that's final position minus initial position, which is 0 over time. Anything 0 divided by anything is 0. Okay, that's 2 of the things we can calculate off of this graph. Okay? Because we can read all of this stuff and just plug it in. I can also calculate total distance and average speed off of this graph. So, how far did this object go? We know its displacement is 0, but its distance is something else. Think back to the Walmart trip.
40 meters.
Okay? What do you guys think? In this trip, we didn't go anywhere, and then we went from 20 to 60. That's 40 meters. How far did we go here? You guys told me that in this part, the object is not moving. Okay, so that would be 0 meters. And then how far was this? 40. How far did we go in total? 80 meters. Okay, just like the Walmart trip where it was 4 kilometers to Walmart, 4 kilometers home. My total distance was 8 kilometers. My total displacement was 0. Okay, so if I want to calculate total distance, I got to figure out how far the object goes in each section. Okay, calculating each section is just doing final position minus initial position for that section. Okay, 60 minus 20 is 40. Okay, 20 minus 60 is 40. Okay, I don't care about which direction it is if I'm finding something scalar like distance. Okay, now that I have my total distance, 80 meters, can I calculate the average speed? I can. Average speed, remember, is total distance divided by total time. That's going to be 80 meters divided by 6 seconds. Okay, so we're looking at 13.3 meters per second. Okay, those are the things we can calculate off of that graph. All right? Everyone okay with that? All right, so we can calculate displacement, distance, average velocity, and average speed off of this graph.
When your graph kind of just ends right up there, do you just assume it ends there, or will it end?
Well, for what we know, it ends there. Yeah, I mean, if it goes further than that, we can't do anything about it because we can't read it.
Okay.
Yeah, so we would assume that that would be, the end of it. All right, now, with this graph, this is still a position versus time graph. What is it showing the object doing? Is it moving? Okay. Is that movement look the same as the first graph? Okay. So what I need, this is the skill we want you guys to develop, is to be able to look at a graph and then interpret. Okay. In the first second, the object goes from a position of 0 to whatever this is, probably like 1. Okay. So not very far. But in the next second, it goes from like 1 to 9. Okay? So in the first second, it only went 1 meter, but in the next second, it went 8 meters. Okay? And the second after that, it goes even farther. It goes from like 9 to 18. Okay? And then the second after that, it goes even further, and that trend continues. In each equal time interval, the object travels farther than it did the second before. Okay, so what is that object doing?
Like picking up speed maybe?
Yeah, exactly. It's accelerating. It's picking up speed. The only way you go further in the same amount of time is to go faster. Okay, so this object is accelerating. Okay, it's going faster and faster because it's going farther each time interval. So anytime you see a curve on any kind of graph, it means that the growth of what's ever on the y is increasing. The rate of its growth is increasing. Okay, does everyone kind of follow me there? When we're talking about position and time and velocity, it means the object is going faster. Okay, or accelerating. Okay, everybody all right with that? Could I calculate from this graph, from the second graph, the one on the right, what is the total displacement of this object? is how we calculate displacement. Right here. So what's my final position? 50 meters. Okay, what's my initial position?
0.
Right. So how far did this object go?
50 meters.
Right, its distance and its displacement for this graph are equal. Okay, it didn't change direction, it always went forward, so the displacement and the distance are both 50 meters. The displacement would be positive 50 meters. Okay, everybody all right with that? Okay. All right, so back in Math 10, okay, you probably learned all about slope. Okay, now sometimes people get taught slope this way. Okay, when they get taught rise over run, okay, which usually means y2 minus y1 over x2 minus x1, okay? And there's absolutely nothing wrong with that. That is how you calculate slope. We don't use that in physics, okay? For this reason. Oh. Hey. Yep. Okay, Mrs. Williams wants to do registers. Okay, we don't do this way in physics for this reason. It only calculates slope. This formula is only good for one thing. Okay, but this formula can calculate more. Okay, can it calculate slope as well? It can. What part of that is slope? The end. Okay. So if I manipulate this formula to solve for slope, I'm going to subtract b from both sides, and then I'm going to divide both sides by x. Is everybody okay with that? All right. Same formula? It is. Okay? If I had this line going all the way to the y-axis, okay, this would be b, right? My y-intercept. Everybody okay with that? And then this up here would be y, and this would be x. Okay, so when I go y minus b, am I also calculating the rise of the graph? And when I go over x, is that the run of the graph? It is, okay? Now, the reason we want to use y equals mx plus b is we can use it to calculate y values, x values, okay? It does more than the rise over run formula does. It's easier to manipulate than the rise over run formula. Okay, so we're going to use it quite a bit more often. This is another skill that we want you to be able to transfer to basically any graph. Okay? One of the skills we need to be able to do is to look at a graph and be able to determine what does the slope represent. Not what is it, we can calculate that. Google Sheets will put it on the thing for you. Okay, we saw that on Friday. But we got to determine what does it represent. Okay? Slope is always the rate at which y changes over x. But what you have to look at on your graph in particular is what's on the y-axis and what's on the x-axis. Okay? On this particular graph, position is on the y-axis, time is on the x-axis. Okay? So that means that on this graph, y is my final position. What's b? Since it happens at time 0, it would be my starting position or initial position. Okay, and what's on the x-axis? Time. So when I do this formula for this graph, here's what I'm really doing. What does that calculate?
The slope.
Yep, but what does the slope represent? What when I go final position minus initial position, what do I calculate? Right, when I go final position minus initial position, I calculate the displacement. So, when I go final position minus initial position and divide it by time, what am I calculating? What equals d over t? Velocity. So the slope of the line on this graph represents the velocity of the object. Okay, so on this graph and the slope. Okay, if I was looking at a different graph, like one of, well, let's say we had one that looked like this. Okay. Should you buy those shares? Why not?
So tanking.
They're tanking, exactly. Okay, that means we can interpret a graph, that's good, okay? I don't wanna buy those shares, they're gonna be worth nothing in a certain amount of time, okay? What would the slope of that line represent then? Okay, what did we say was happening to the value of those shares? It's going down, okay? Would that tell me the rate at which those shares are going down? In dollars per week. Okay, because if I calculate the slope of this line, okay, I go y minus b, okay, over x, I'm gonna have 0 minus whatever this is, let's say it was $100, okay? 0 minus 100, and let's say this was like 10 weeks. Okay, well, they're going down by $10 per week. Okay, so after 10 weeks, well, you better hope you don't own any. It won't be good for anything at that. Everybody all right with that? So every graph, the slope represents something different. Okay, in this case, the slope was the value of shares per week. Okay, on a position versus time graph, the slope is the velocity of the object. On a velocity versus time graph, it's the acceleration of the object. And I'm not saying you need to memorize that. I'm saying you can interpret that from every graph. Okay, that's the skill we want you to have, because as I said, you get to physics 30 and you got 36 different graphs you gotta know. You're not memorizing what the slope of every one of those 36 graphs is. Especially if you're taking chemistry at the same time where you got another 24 graphs you gotta remember. Okay, don't memorize it. We want you to be able to analyze it. Okay, if I do this, okay, this is in dollars, this is in weeks. My slope is in dollars per week, and it's negative, okay, this is going down by $10 per week. Okay? All right. So, here's something I would totally ask you to do on a quiz or a test. Okay, doesn't require any calculating. What is the object doing in part A? Okay, going up, if this is up and down, going up. Going up in what way?
For 2 seconds.
Okay, it goes up 6 meters in 2 seconds. Okay, we're getting close. These are both right, they're both right, but I'm looking for something a little bit more specific. And the 6 and 2 is gonna get you there. This went 6 meters in 2 seconds.
3 meters per second.
Right. This is moving up at a constant velocity of 3 meters per second. That would be your full mark answer. Okay, because that says, I recognize this is a position versus time graph. I recognize that the slope of this line is velocity. It's in meters per second, and this thing is going in a diagonal line, which means it's constant. Okay, all right, what's the object doing in part B? Nothing. Okay, now on a test, don't write nothing. Like literally, if you write nothing, you won't get anything. Okay, also don't write the word nothing. Okay, the object is standing still. Okay, or you could say the position is not changing. Okay, or you could even say not moving. That would be fine too. Okay, all right, what's going on in part C? Let's start out with which direction is it going? It's backwards. Yeah, it's going backwards. Okay, is it going backwards at a constant rate? Okay, and that constant rate is a constant, starts with V. What's this? Velocity. Okay, this thing is going backwards at a constant velocity. Okay, what's it doing in part D? Standing still, not moving, okay, something like that. Okay, in part E, what is it doing? Okay, which way is it going? Up or forward, yeah. Is it doing that at a constant rate? It is, because it's a diagonal line, it's not a curve, okay? So it's moving forwards at a constant, starts with V, velocity. Okay, we could say we can always say rate. Rate is always true, but it's not terribly specific. Okay, rate would apply to any graph. Okay, but velocity applies specifically to this one. All right, if we're looking at E and F, in both E and F, the object is moving at a constant velocity in a forward direction. Which part's faster, E or F? A few minutes ago, you guys told me the slope of a line on this graph represents velocity. Okay, E because it covers more ground in less time. Yep. E because the line is steeper. Yeah. Okay. Steeper line means going faster. Okay. Because that's the slope is in meters per second. The steeper the line, the greater the meters per second. Okay. Those are the kinds of things I would ask you to interpret from this kind of graph. Now, here are some things I want you to try and calculate. What's the total displacement of this object over the entire 18-second trip? I should have my answer already. 0. What's my initial position? 0. What's my final position? 0. Okay, my initial position and final position are the same place. My total displacement is 0. Okay. What's my average velocity over the whole trip? 0. Yeah. Because velocity is displacement divided by time. And the displacement was 0. Okay. If displacement is 0, velocity is also 0. Okay. This one's going to take you a little bit longer. I want you to calculate for me the total distance traveled by this object. Okay. That's one part at a time. Okay, calculate how far it goes in each part, and then put them all together. Okay. Oh, okay. That's a good question. Huh. Okay, how do I go in negative meters? Okay. Let's say I start right here. Okay, so I walk forward 3 meters. I walk backward 4 meters. I'm negative 1 meter behind where I started.
Okay.
Right? So in this graph, the object moves forwards, then stops, and then goes backwards past where it started to another point. So exactly what I did, except like way further, so I have to start here, walk to the wall, and then walk backwards to this. And then I'd be doing exactly what that graph was doing. And then stand at my desk for a second or two, and then move forward again.
Okay.
Does that make sense?
Kind of.
Okay, so it's not that, I mean, yes, I went negative meters,
Yeah.
but it just means that I ended up behind where I started.
Okay.
So I started in Okotoks, I drove to Calgary and then drove to High River. Well, I ended up south of Okotoks, that can be negative,
Okay.
yeah? Okay, who thinks they got it? Okay, let's figure it out here. In part A, we go from 0 to 6 meters. How far do we go? 6 meters. How far do we go in B? Nothing. Okay, in part C, we go to negative 10 meters from 6 meters. How far is that? 16 meters. Okay, because we go 6 here and another 10 here for a total of 16 meters. Remember, distance is scalar. It doesn't care whether I went backwards or forwards. Okay, I started at 6 and went back to negative 10. All right, how far do I go in D?
0.
All right, and then in E, I go from negative 10 to negative
6.
4. So that would be 6 meters, and then this would be
4.
4, because we go from negative 4 to 0. Okay, 32 meters. Okay, there's my total distance traveled, 32 meters. Even though my displacement ends up being 0, because I ended up back where I started. Okay, you see, still scaling table. Okay, so here's what happened in this one. Okay, this is going to be my initial position, so I'm going to mark it with that. Okay, I go forward 6 meters, and then I stand here for a little while and do nothing. And then I back up 16 meters. And then I stand here for a little while. This would be part D. And then I go forward fast, and then I slow down for the last 4 meters, and I end up right here, back where I started. It's weird sometimes to see it actually done and then look at what the graph looks like. And it takes a little while to be able to go, okay, I can visualize what happened. And that's where we want to get. Okay, so my total distance is 32 meters. Total time is 18 seconds. What's my average speed?
I have a question.
Okay.
So you don't do 6 minus 16, you just add them all?
Right.
Okay.
Yeah, for distance, because it's scalar.
Yeah.
Okay. How do we calculate average speed? Total. These are things we gotta know. Speed is total distance divided by total time. We just calculated the total distance to be 32 meters. According to the graph, the total time is 18 seconds. Okay, 32 over 18 is gonna be like 1.8 or something, 1.9,
1.77.
1.77. Average speed is 1.77 meters per second.
I got a different number. It's 2.33.
32 over 18?
Yeah.
Can't be. Okay, questions on what we did there? All right, now this one's tricky for interpretation. Okay, get it better. Okay. So in this graph here, okay, we got a whole bunch of curves. Okay, so what's the object doing between time 0 and, right here, so about 11 seconds. It's accelerating, yeah. It's speeding up. Remember, if it was a diagonal line, it would be increasing its position at a constant rate, or traveling at a constant velocity forwards. But here, it's going faster and faster and faster, okay? And we know that because each time interval, the distance it travels gets bigger and bigger and bigger, okay? Until we get kind of to here, okay? Everybody all right with that? Okay. What's it doing here between here and here?
Decelerating?
Yeah, it's slowing down. All right. How can we tell that? So like here the line's getting steeper and steeper and steeper because the object's going further each second, going faster, okay? But here, the line starts to get flatter, okay? And then once I get past B, the line starts to get steeper again until about here, and then it starts to get flatter again, okay? So over this part of the graph, the object slows down and then for an instant stops and then speeds up in the other direction. Okay? And then at the end, we can see that it's slowing down and coming to a stop because the line gets flat again right at the end. What does this graph up? Graph of that. Okay? During part A, it's accelerating. That's when I'm throwing it up in the air. It's going faster and faster and faster. As soon as it leaves my hand, what's pulling on it? Gravity. Gravity slows it down, slows it down, slows it down, stops for just a second, and then pulls it back down the other way. That's why the two halves of this thing are identical. They're both gravity. In one case it's moving up and slowing down, in the other case it's moving down and speeding up. It's the same acceleration. Okay? And then here where it's flattening, where I catch it, bring it to a stop in my hand. I would never ask you that on a test. That is totally unfair. Okay, to say, here's a graph, what is it? No. Okay, but can we interpret it and say what was happening in each part at least? All right, so anywhere where you see the curves, okay? The curves mean that there's a non-uniform change in whatever is on the y-axis. For a position time graph, that means the object's velocity is changing. Its rate of change of position is increasing, okay? All right. Now, before we get to those, they're there, so you can check and see if you did them right, okay? It'll give you guys a little bit of time to work on that. Okay. So it's in your digital workbook and it's at the bottom of page 3 of the physics workbook. Okay, so if you want to have it on your phone, that's where you can find it. Okay, so we got this position versus time graph tells us where the object is at various points in time. Okay, we want to find the total displacement. All right, so the first thing I got to remember then is that total displacement is final position minus initial position. Okay. Now, my final position, according to the graph, is 0.5 meters. My initial position, according to the graph, is 0.2 meters. Okay, 0.5 minus 0.2 is 0.3 meters. Okay, and that would be positive because it went up. Okay, everybody all right with that? Okay. That's all there is to calculating displacement from position time graph. Okay, I gotta read the graph to get the final position, read the graph to get the initial position, then subtract. That's it. Okay. All right, now, the next thing it wants us to calculate is the total distance. So that's section by section. How far did it go in each part of the graph? Right? Well, this part's easy. How far did it go here?
It didn't move.
It didn't move. This was 0 meters. Okay, here it went from 0.2 to 1.0. How far is that? 0.8 meters. Okay, how far did it go here? 0. Okay, and then from here, it went from 1 down to 0.5. So how far did it go there? 0.5. Okay, it doesn't matter that it was backwards, we're just calculating distance right now. Okay, so 0.8 plus 0.5, because scalar quantities only get bigger, okay, is 1.3 meters. Okay, so I gotta do a little adding, a little subtracting, okay, but nothing super serious. Okay, for part C, average velocity over the whole trip. Okay, so average velocity equals total displacement divided by total time. Okay, that could also mean final position minus initial position over time. Okay, I already did that calculation, so actually I already know what it is. Okay, but we can punch it in again. We can have 0.5 minus 0.2 divided by 7 seconds. Okay, so we're looking at 0.04 meters per second. And that would also be positive, okay, because velocity is a vector quantity, and I need to establish a direction on that. Okay, and then the last one is average speed of the object. Okay, so V equals d over t. Okay, so speed equals total distance, which we already calculated to be 1.3 meters, divided by total time, 7 seconds. Okay, that should give us 0.19 meters per second. Okay, we don't put a positive on that because speed is scalar. Okay, so are these problems a whole lot different than the word problems we did before? They all use V equals d over t, right? Okay. Graphing problem and a word problem work pretty much the same way. You just get the data in a different way. Instead of getting a story with the data in it, you get a graph with the data in it, which is probably easier than having to read the story and get out the meaning from there. Okay. All right, I'll back it up here. Thought I had position time graphs on there. Guess I don't. Okay, we'll go forward again. Okay. Give this one a try. I apologize for the poor quality here. This is 0, 20, 40, 60, 80, 100. Sorry, when I upgraded to the new panel, all my 1080 stuff got really crappy. Okay. All right, so give this one a try. Pretty much the same as the last one. Okay, same idea. So first thing we want to do is find the distance traveled. So scalar quantity, doesn't matter which direction. Okay, the distance traveled between 0 and 90 seconds. All right, so what I want to do first is establish my initial and final positions. That's my initial position. Okay, and 90 seconds is right here. Okay, so my final position is 200 meters. Okay, my initial position is 0, but this is looking for distance, so I actually have to calculate each part. So in this first part here, we go from 0 to 400 meters. So how far did we go? 400 meters. Okay, and then how far did we go here? 0. And then from here we go from 400 to 200, which is another 200 meters. Okay, what's my total distance? 600 meters. Okay, the displacement from 20 to 80. Okay, so I'm just going to erase all that stuff that I just drew on there. Okay, so now my initial position is here at a time of 20 seconds. Okay, and my final position is here at a time of 80 seconds. Okay? So if I want to find displacement, that's final position minus initial position. Okay, my final position at time 80 seconds is 300 meters. Okay. And my initial position at time 20 seconds is 200 meters. Okay. My displacement is positive 100 meters. Did I travel further than that during that time? Yes, but my position only changed by that much. All right, speed over the whole trip. All right, if I want speed over the whole trip, then I'm going to need the total distance over the whole trip. Okay, so we already established that this was 400, that this was 0, and then we go from 400, or from 400 back to 0. So how far do we go here? 400. Okay, so my total distance over the whole trip is 800. Okay, and the total time is 100 seconds. Okay, so V equals D over T, 800 over 100. Okay, that's positive 800. Should give me positive, or not, sorry, that's supposed to be speed, not. Okay, speed over the whole trip is just going to be 8 meters per second. No direction number. All right, now velocity over the whole trip is easy because my final position is 0 and my initial position is 0. So my total displacement is 0, and thus my average velocity is 0. See it? Okay. All right. How are we feeling about that one? Okay. Those are really not much different than what I would ask you on a quiz, okay, or a test. Okay. Here's a graph. Interpret some stuff. Okay. And I might ask just very simply, what's happening between 0 and 400 seconds? Or sorry, 0 and 40 seconds. Okay. What's that object doing between 0 and 40 seconds?
Going up 400 meters.
Okay, going forward 400 meters at a constant, starts with V velocity. Right, that would be your full mark answer. Okay, like I would probably make that 2 or 3 marks. Okay, if you said going forwards, I might give you 1 mark. Okay, if you said going 400 meters forwards, that might give you 2 marks. And if you said going 400 meters forward at a constant velocity, then I'd say awesome, that's exactly what I'm looking for. Okay, you guys follow the difference between those answers? Okay, because one tells me I can kind of see what's happening. The other says I can calculate what's happening. And the other says I'm interpreting everything and giving you the general trend here. Okay. Okay, so this one goes down into the negatives. Does it change what you do? No. All right, just so you can see things better, okay? 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. Okay, and that's an 8, not a 0. All right, give you a few minutes on that one. All right, so part 1 wants the displacement from 0 seconds to 4 seconds. All right, so that means that this is going to be my final position, and this is going to be my initial position. So to get total displacement from 0 to 4 seconds is final position minus initial position. So we're looking at -4 minus 0, which is -4 meters. Okay, everybody all right with that? Okay. Is it okay that that comes up negative? It just means the person walked backwards. Okay, that's fine. All right, total distance traveled, okay, for the whole trip. All right, so that's what we were talking about just a minute ago here. In this first part here, we go from 0 to -4, so that's 4 meters. We don't go anywhere during this part. And then we go from -4 to 6, okay, which is another 10 meters. Right, so 10 plus 4 is 14 meters. No sign or direction on that because it's scalar. Okay, C, average speed over the whole trip. Well, I just did all the heavy lifting for that. Okay, just calculated the distance, so that saves me a ton of time. Okay, speed equals distance over time, 14 meters divided by 7 seconds. How did I get 2.3 for that? Oh, because it stops at 6. That's why. Because I can't read my graph. Okay, 14 over 6 should give me 2.3 meters per second. Yeah, not 7 seconds, 6 seconds. Okay, and then average velocity over the whole trip. Okay, so average velocity is total displacement divided by total time. That's going to mean final position minus initial position divided by time. My final position is positive 6 meters. Okay, my initial position is 0. Okay, and then the total time is 6 seconds. Okay, which is going to give us positive 1 meter per second is the average velocity. Okay. All right. I put one on the unit exam last year that looked like that, except it was flipped. It went positive and then negative. Like, I'm not going to ask you to do anything tougher than that in terms of interpretation and calculation. Okay. No, that's velocity versus time. Okay. So tomorrow, we're going to do a lab with these little carts. Okay, we're going to push them along the floor and record their position, okay, as a function of time. And then we'll build some position versus time graphs with Google Sheets and do some y equals mx plus b calculations like I told you on Friday, that multi-run graph. Okay, that's what we're going to be doing. And then Wednesday, we'll get into velocity versus time graphs. Okay, and then we'll keep going from there. So we're doing pretty well so far, guys. Okay. Good work today. I'm going to quit there because you guys worked hard today and I can't start something.